Hi everyone, in this video we are going to be talking about every single periodic trend that you're going to need to know. So I'm going to start with atomic size. Now, as you go down a row, the size gets bigger. So the general rule is fluorine is the skinniest atom there is. Francium, if you go to France, you're going to eat all of the pastries and you're going to get really fat. So francium is our fattest atom. So if we are comparing, cobalt to phosphorus, and I were to ask you who has a bigger atomic radius, whoever's closer to fluorine is smaller. Whoever's closer to francium is bigger. If we want to get more in depth, we can talk about how each row is another energy level or another shell of electrons added. So because hydrogen's in the first row, hydrogen will only have one shell, lithium will have two, sodium will have three, potassium will have four. Okay, exaggerated, but you can see that as you go down, it gets exponentially bigger. Now, as we go this way, why does this get smaller? It's actually because of something called the shielding effect. I'm going to quickly talk about the structure of an atom really quick. So this is based off of the Bohr model of the atom. Let's talk about sulfur, for instance. Sulfur is in the third row of the periodic table, so he's going to have three shells. The innermost shell is going to have two electrons, and then every single other shell of electron is going to be eight. So he is going to have 1, 2, 3, 4, 5, 6, 7, 8. That's 10 right there, okay? But he has 16 total electrons. This here is our atomic number, okay? Atomic number is the number of protons, but typically if we don't have a charge, the number of protons equals the number of electrons, which equals the number of neutrons, okay? So we are looking at a neutral sulfur, it has 16 electrons in total. So this is also telling me that he has 6 valence electrons. So he has 1, 2, 3, 4, 5, 6. Is that outer shell a full shell? No, he has 2 open spots left. Those are called his valence electrons. He has 6 valence electrons and he has 10 core electrons. Now, when you subtract that, that's when you get, shielding value. That's really what the shielding effect is that these core electrons are kind of shielding these outermost electrons from that pulling effect of that positive nucleus, okay? Your core electrons are shielding your valence electrons, and that's what causes the other atomic size trend. A quick way to remember, the amount of valence electrons, everything in row 1 has 1 valence electron, everything in row 2 has 2 valence electrons. Everything here, all these guys have 8 valence electrons. That is why they are called noble gases. They have a full octet. Every single one of their outer shells are full. In group 17 or group 7A, these guys all have 7 valence electrons. 6, 5, 4, 3. That's how many valence electrons all of these have. So this is actually where I want to bring in the ionic radius trend, okay? So let's say we are comparing sodium versus sodium plus 1. An electron has a charge of -1. So if sodium has a plus charge, did he gain an electron or did he lose an electron? He lost an electron. You removed a negative and he's left with a +1. So let's quickly draw out sodium. He's in the third row. So he has 3 shells and he has 11 total electrons. But really, how many valence electrons does he have? 1. We're going to draw it completely. So we have 2 and then we have 8. And then 11. So that was 10, and then 11 is that one valence one. Now, that is sodium, just plain old sodium. Sodium plus 1 is when we remove an electron. What does this look like now? That's what that looks like now. So my question to you, did this get bigger or did this get smaller? It got smaller. As you remove electrons, it gets smaller and smaller and smaller. Something that you need to know about electrons is that they repel each other. If you put a negative charge and a negative charge, they repel each other, okay? Positive and negative attract, negative and negative repel. So if, for instance, I were to throw another electron in here, all of these electrons, they're all negative. So they are like, get the frick away from me, get out of my space. They're repelling each other. And when you add another negative charge in there, it starts to spread out more and more and more and more because they're like, get away from me. I need my space. You know what I mean? Anyways, so if we have sulfur versus sulfur with a -2 charge, that's really going to just be this guy. And then we're adding those two electrons, and all these electrons are repelling each other. Okay. So it's getting bigger and bigger and more spread out. So that's going to be my trend when it comes to ionic radius. So let's say you were asked to rank potassium, calcium, and then let's say selenium and bromine. Okay. If you had to rank these in order of size, atomic radius, the absolute smallest are the ones closer to fluorine. This is closer to fluorine. Then it's this one. So this guy is the smallest, then him. That then closest to francium is that. So potassium would be our biggest here. But if you are asked a question and you are asked to rank it based on ionic radius, if you are given, now rank K plus, Ca 2 plus, selenium -2, and then bromine -1, you can only use the periodic trends when you're looking at things with the same charge. So if I had to rank bromine -1 and selenium -1, then yeah, bromine would be smaller because, they're on an equal playing field now. However, now we're ranking based on what's going on with their electrons. Okay, as we said, when you remove an electron, it gets so much smaller. You can picture that with that sodium. When you remove that valence electron, it became so much smaller. So if we remove one electron versus if we are removing two electrons, they're both getting smaller, but who's getting more small? This guy would be our smallest. Why? Because we are removing two. Now, when we look at these guys, if you are adding one electron, we know that electrons repel. So if I add another electron in there, they're all like repelling each other. All right. They're already a little bit bigger. Now, if I add another electron in there, they spread out even more. They're flying away from each other like a balloon. They are like, get out of my space. So this guy would be the largest. Why is he the largest? Because we added two electrons and they repel each other. So they're going to spread out. Does that make sense? Okay. Ranking in order of increasing radius. Increasing. So we are starting small and we are getting to the biggest. Now, if we were just ranking these plain old atoms, nothing special going on, the absolute smallest would be bromine, then it would be selenium, and then it would be calcium, and then it would be potassium. But if you had to rank them taking into account, ionic size, now our ranking has changed. I know that my two smallest are going to be the ones with the positive charges. Now it's going to be calcium with a +2, potassium with a +1. And my biggest ones, we are going to have bromine with a -1, and our absolute biggest is going to be selenium with a -2 charge. Now let's talk about electronegativity. How much do you want that electron? Okay, so I'm going to just zoom in here and we're going to focus on fluorine and oxygen. Fluorine has 7 valence electrons. And oxygen has 6 valence electrons. So I'm going to just kind of draw that here. You'll learn about this another time, but I really, really like to have the visuals here. They want a full octet. I kind of think about electronegativity as like, how is that atom for an electron? How badly does he want it? Okay. Fluorine, he is so freaking close to an octet. He's basically there. He is like, if he sees anyone with an electron hanging out of their pocket, he's going to attack them and steal it. He wants it that bad. Now, oxygen, yeah, he's really, really close to that octet as well. He really wants it bad, but does he want it as bad as fluorine? Not really. Like he still wants it, but does he want it as much? No. So that's why I want you guys to think of fluorine as the smallest and the most electronegative, or the most atom. Who's more electronegative? Silicone or chlorine? Chlorine. Duh. Now this brings me to our next topic called electron affinity. So if we are considering electronegativity as, how badly do they need it? I like to think of electronegativity as, how big of a release will our atom have when he finally gets that electron? So I want you to think like fluorine is literally so close. So when you give him that electron, he is going to have a huge release. You think he has a huge sigh of relief, okay? He got it. He can take a breath now. It's done. Like, oh, wow, that felt great. Like, thank you so much. Like a huge release, okay? Now, oxygen, when he gets an electron, he's like, wow, that felt so good. Still like had a release. Did he have as big of a release as fluorine? No, because he like still needs a little bit more. You know what I mean? So when we're looking at electron affinity, that's directly related to how electronegative are you? How much do you want it? That's how much relief you're going to have when you gain that electron. And electron affinity is actually a negative number because it's a release. It gains this electron and it releases energy. That's what it is. Electron affinity is the amount of energy released when they gain that electron. Ionization energy is how much energy it takes to pry one of their electrons away from them. With fluorine, you would have to pry one of his electrons out. He's like, no, I'm so freaking close to an octet. Don't touch my electrons. He's going to have a pretty high ionization energy. Then we're going to come to the front of the periodic table and we're going to look at, sodium. Sodium has one valence electron. If I were to draw sodium out, what's easier for sodium to get his full octet? For him to go around and find 7 people to give him an electron, or for him to just give one away? So much easier for him to give one away. Now, this is why our metals tend to become cations because they give away an electron, and our nonmetals tend to form anions because they want to gain an electron. It's easier for fluorine to just gain one electron than find 7 people to give each electron away to. Okay, so sodium, he's like, oh, I'll give it away, but it doesn't just fall off. You still need to add a little bit of energy to take it. So like for you to take this one electron, he's like chilling. He's like, okay, like you could take it. It might take like 100 joules of energy. Not too bad. If we look at calcium, I'm just going to draw it like this too. That first ionization energy, he's like, yeah, like take it. It's fine. And same with the second one. So ionization energy 1 of calcium is going to be like also like, we'll call it like 200. Ionization energy 2, he still wants to get rid of it, but it is going to take a little bit more energy to remove it now. All the valence electrons are gone. This is what we're left with. After ionization energy 1 of sodium and ionization energy 2 of calcium. Now, are these valence electrons anymore? No, these are their core electrons. So if I want to take this, it is going to take like 5,000 joules of energy. We took sodium's valence electrons away. So he's like, great, now I have an octet. But now we're trying to pry away one of his core electrons. He's like, no, don't you dare. Don't you dare. I'm fine. Don't touch me. So we are going to have a huge jump in ionization energy. Same thing with calcium. If I try to remove this electron, so this would be ionization energy 3, this would cost like 7,000 joules or something. I'd have to put in so much more work to get this guy out. So if you had to rank first ionization energies, it's still going to be that same general trend. A lot of times you are going to be given, ionization energy 1, 2, actually, I have an example about this. Let's kind of just look at these. They're really just increasing by like 1,000 to like a little over 1,000 each time, right? There's no huge jumps. Look here. Wow, that went from like, we're going to call this 9,000 to 27,000. Did that jump like 1,000? No. That was triple the amount of energy. That was triple the amount of energy. So what is this telling me? This is telling me that this is my core electron. So how many valence electrons did I have? You had 6 valence electrons. Now it's asking you what period 3 element has the following ionization energies. The period is just the row. So now we are going to look at the third row and see who has 6 valence electrons. Out of these, who has 6 valence electrons? Sulfur has 6 valence electrons. So what element is this? It's going to be sulfur. Why? Because we removed all 6 valence electrons. And then that is telling you that the 7th is his core electron. Last trend is metallic character. This is the metals. These are the nonmetals. It's just the same way. This is our same trend for metallic character. Fluorine is not a metal. Fluorine is as non-metal as it gets. Okay, so if I had to rank the metallic character of like these guys again that are highlighted, the most metallic Also, the biggest is going to be the closest to francium. The least metallic or the smallest is going to be closest to fluorine. Okay, it's same trends there. That is it for this video. I hope this helped and good luck with all your finals.